Hello, this is the remaining two examples from the section 4.5 graphing rational functions. We had two of them that we did not get to in class, so I'm going to scroll down and work through those together so that you can check and see if you have grasped the concept of graphing rational functions. I highly recommend you try them on your own first and then watch the video. So this is example E, f of x equals 2 over x plus 1 squared. And we need to write everything that we need to know, just like when we've done any of these. So I'm going to make this a little bigger so I can write a little more clearer. There we go. So starting with this example, I need to know the domain of the function. That was one of the things we wanted to know. We want to know if there are vertical asymptotes, if there are holes, if there are x-intercepts, if there's a y-intercept, a horizontal asymptote, or an oblique asymptote. So remember, the first step to figuring out any of these pieces is to look at your function and ask if it's factorable, if there's anything you can break apart. This has already been pre-factored essentially for us. So the only thing that could cause us any issues in our domain is x equal to a -1, because that would cause us to divide by 0. And that is not something that is canceling out with anything on top. So that means that is also our vertical asymptote. So remember, anything in the bottom that has an x that doesn't cancel out with anything on top causes a vertical asymptote, which is an equation of x equals that number that makes that factor equal 0. Holes are things that happen when some factor on top cancels with some factor on bottom. That's called a removable discontinuity. We do not have anything canceling, so that means we have none for holes. We also do not have any x-intercepts because you must have a factor of x on top after reducing, and we have no x's in the numerator. And that is after you've canceled or reduced. That's when you check that. The y-intercept, you plug in 0 for x. So 2 over 0 plus 1 squared is going to be 2 over just 1, because 1 squared is still 1. So that is 2. So 0, 2 is where we're going to cross the y-axis. And then remember to determine your horizontal versus oblique, because you cannot have both. You're really comparing these degrees of the top or your numerator to the degree of your denominator. So there's no x on top, so the degree of the top is 0. Now on the bottom, you might say the degree is 1 if you look at the x, but if this was FOILed out, this would be x squared plus 2x plus 1. So the degree of this one is actually 2. So when you have a function where the top has a degree smaller than the bottom, that is the horizontal asymptote y equals 0. Now if you tried to do long division here, first of all you'd have to FOIL out the x plus 1 times x plus 1, and then you would be trying to divide it into 2. Well, x squared can't go into something that has no x, or even an x smaller than it. So that is why we get it goes 0 times. That means there's none for the oblique. So we want to go ahead and dash in all of our asymptotes. So at -1, we're going to dash in a vertical asymptote and label it all the way down. At y equals 0, we have a horizontal asymptote. The only point that I was provided with from the information is 0, 2 is my y-intercept. So we're definitely going to need a table of values to find some more points. Now remember, when we were in class, we discussed how you want to use points that are on either side of either x-intercepts or your vertical asymptote. So we only have a vertical asymptote, so we're going to look for points on either side of -1. I'm probably going to pick 3 points on the left side since I have nothing over here, and just 2 more points on the right side. So on the left side, I'm going to do -2, maybe -3, and maybe -4. On the right side, I already have 0, so I'm going to do 1 and 2. And remember, we are just plugging these into our function and working it out. So this is 2 over -3 squared, which is 2/9. If we plug in -3, this is 2 over -2 squared, which is 2 over 4, or 1/2. Notice we're squaring, so everything's turning out positive. 2 over -2 plus 1 squared is 2 over -1 squared, which is going to be 2. We plug in 1, That is 2 over 2 squared, which is going to be 1/2 again, because you're going to get 2 over 4. And if we plug in 2, we get 2 over 3 squared, which is 2/9. Now, if I plot these, you'll notice that on both sides of the vertical asymptote, our graph is going to be above the horizontal asymptote. And that's happening because the bottom is squared, so you're never getting a negative value for your fraction. All right, so this one is hovering in the top region on this side of the vertical asymptote, and on the other side, we're also in the top region. So these are actually very symmetric to each other because of that squaring. Okay, so that is the graph for part E. So let's look down at G, which is the last one. This is probably the most involved one. It is not factored, so we have to do that first. So this would be x minus 4 and x plus 1. Multiplies to -4, but adds to -3. This would be x plus 3 and x minus 2. Multiplies to -6, adds to 1. So we need to know domain, vertical asymptotes, holes, x-intercepts, y-intercept, horizontal asymptote, or oblique asymptote. So remember, domain is before you look for any cancels. So x cannot be -3 or +2. And it just so happens nothing cancels. So that means both of these guys are going to be vertical asymptotes and both of these are going to be x-intercepts. We only get a hole if something cancels out. So we're going to have x equals -3 if you solve this one, and if you solve x minus 2 equals 0, you'll get x equals +2. Holes would be none. X-intercepts, you need to solve both of the top factors for 0. So if you have x minus 4 equals 0, that gives you a +4. And x plus 1 equals 0 would give me a -1. So we're going to cross the x-axis at 2 different locations. To find our y-intercept, you plug in 0 for your, and I usually do the original function. It just goes a little quicker as long as 0 is not an asymptote. So this would be -4 over -6, or 2/3. So 0, 2/3. Also, if it's easy to see the horizontal versus oblique from the original, I go back to that. This is a degree on top that is 2, and a degree on the bottom that is also 2. When the degrees match, it is the leading coefficients in front of those terms. So y equals 1 over 1, which is just 1. Now, you could do long division to prove that as well, but if you have matching degrees or your degree on top is smaller, you're horizontal, which means your answer is just a number. And if you have a higher degree on top than bottom, you are going to have the oblique, and the only way to find the linear oblique equation is to do long division. So now we're going to be looking at graphing this one out. See how much information we have. So we have a vertical asymptote at -3. So we need to sketch that in. And one at +2. We also have a horizontal asymptote at y equals 1. Okay, now we want to plot all of our points. So 4, 0 is going to be an x-intercept. -1, 0 is a x-intercept. And 0, 2/3 is a y-intercept. I'm very cautiously thinking that we might be in trouble here and we might cross our horizontal asymptote just by the way these points are going up. So I am going to do the test for that on this one. Remember I said that I always put a couple in the examples, even if we don't test you on crossing, just so you can see how it happens. So if you set your horizontal asymptote equal to your reduced function, which in our case it didn't really reduce, so you can just set it equal to the original. My horizontal asymptote was 1 over 1 essentially, because you want to make it a fraction. Set it equal to x squared minus 3x minus 4 over x squared plus x minus 6. So what we're checking here is, do we cross the horizontal asymptote? Because I'm kind of suspicious the way this point's headed up towards that red line instead of away from it. It could just come back and turn back around, but I'm suspicious here. So I'm going to cross multiply. So this will be x squared plus x minus 6 equals x squared minus 3x minus 4. When I go to move the x squareds over, they cancel. So that part cancels out. But I still have an x I can try to solve for. So I'll add this over. That would be 4x. Add that over. That'll be 2. I get that this crosses at x equals 1/2. Okay, which is kind of what I was suspicious of because the way this was headed up. So I'm just going to do this ahead of time, and you will get this even if you do your table of values. You'll still see that it crosses, but this is the proof that it crosses. So that's something nice to know, and it helps you really get a grasp on what's going on with the picture. So we need a few more points because we have 6 subregions. I kind of have a little bit of information in the middle. It makes it look like it's stuck in the bottom, but I now know it's going to cross. I think I'm stuck in the bottom on the right side of 2. I have no information yet about the left side of -3. So let's go ahead and plot out a few things. Now remember, when you're picking your points, you want to pick things on either side of your vertical asymptotes, which you have 2 of them, and on either side of any x-intercepts, which we have 2 of those as well. So we've got a lot of things in this one. This is why it's always my last one. And then we need something on the other side of 4, which is an x-intercept. This just helps us break our table up so that we have the best view of the picture. So I have no points to the left of -3, so I'm going to pick at least 2. So we're going to pick -4 and maybe -6. Oh, and by the way, since we solved this and said it crosses at x equals 1/2, that's the only place it can cross that y equals 1. You can never cross vertical asymptotes, and you can only cross horizontal or obliques if you get an x value when doing this little proof here. Okay, so I'm never going to cross anywhere else except at 1/2. And then between -3 and -1, I can only really do -2. Between -1 and +2, I already have 0, so I'm going to do +1. And that's going to show me that crossing I'm going to see in a minute. And then between 2 and 4, I can do 3. And then I'm going to get at least one other point on the other side of 4 since it's in this bottom subregion. So I'm going to pick maybe 6. Okay. So we're going to plug these into our function, and it's up to you whether you plug it into the original or the factored form. I'm going to rewrite the factored form here for myself. Just because factored form might be quicker. I don't have a calculator always handy, so sometimes that's not too bad. Just depends on what you've got available. So this is -6 minus 4, -6 plus 1, -6 plus 3, -6 minus 2. That's a -10 times a -5 over a -3 times a -8. That is going to be 50 over 24, which reduces down to 25 over 12. Okay, and if you want, you could turn that into a decimal. 25 divided by 12 is 2.08, and then there's a 3 repeating, so 2.1 if we want to be rough estimate there. Okay. And then we have -4 minus 4, -4 plus 1, -4 plus 3. We're plugging it back into this, -4 minus 2. So that's going to be a -8 times a -3 over a -1 times a -6. That's positive 24 over 6, and that's going to come out nicely to positive 4. Plugging in -2, so -2 minus 4, -2 plus 1, -2 plus 3, -2 minus 2. This is going to be -6 times -1 over positive 1 times -4. So that comes out to -6 over, or sorry, positive 6 over -4, which is -3/2, which we know is -1.5 if you want to put it in decimal form. Plugging in positive 1. So this one just takes more work because there's more points that we need to really sketch out what's happening around all of those asymptotes and the x-intercepts. So 1 minus 4, 1 plus 1, 1 plus 3, 1 minus 2. Plugging again into this function that we had. So this is -3 times 2 over 4 times -1. That is -6 over -4, and that is positive 3/2. So notice we were down here, but now we're going to go up above the the line 1. So that's that crossing part. And it happens at 1/2. That's where the crossing happens at. So when we draw this, I'll try to make sure I cross through at 1/2. And then for 3, we have 3 minus 4, 3 plus 1, 3 plus 3, 3 minus 2. So that is negative 1 times 4 over 6 times 1. That's going to be negative 4/6 or negative 2/3. Not quite negative 1. And then the last one is 6 minus 4, 6 plus 1, 6 plus 3, 6 minus 2. So this is 2 times 7 over 9 times 4. That is 14 over 36, which reduces to 7 over 18. So again, we're going to be below the line y equals 1. We're not actually crossing it there. So negative 6, 2.1 is about here. Trying to draw it without it erasing it. Negative 4, 4 is up here. So notice on this side of that vertical asymptote, we're staying in the upper region. Negative 2, we're at negative 1.5. So notice this is coming down towards negative infinity. Drawing that the best I can right there. So down. I'm going to cross the line at a half. Remember, that's what we learned from solving that. But that makes sense even if I didn't know that, because 1.5 is right there to lead me up towards positive infinity. So we actually get like an x cubed shape in the middle here on this one. And then the last one, we had that 3 was at negative 2/3. And that 6 is at 7/18. So this one is staying below the red line and going towards negative infinity. So that is the graph of function f of x for part G. All right, so I'm going to be saving the ink on this for everyone, posting this, and I've got the video and it's posted in the announcements for you all.